In last lecture, we have talked about the low frequency response of common emitter BJT amplifier. And this was the circuit diagram of it. The common emitter amplifier, we have seen the significance of the input and output coupling capacitor and also the role of the bypass capacitor. The beta and the VB were the BJT parameters, right? And we have further discussed the DC and the small signal midband analysis, right? Along with the formula. Now we have reached up till, I am not repeating those step 1 to step 4, that was already covered in the last lecture. But in step 5, we have we were in the verge of calculating the low frequency response of the circuit. That is FL, right? And we will see exactly today why it is low frequency response. So for low frequency response, we have to draw the low frequency small signal equivalent circuit and then calculate the lower cutoff frequency due to the individual external capacitors, that is FL of CC1, FL of CC2, and FL of CE. And for this, we have to keep the capacitors in the AC equivalent circuit, and only independent sources will be replaced by a short circuit. So we have come up with this low frequency equivalent AC model, right, over here in the form of capacitor CC1, CC2, and CE are present in the circuit, right? If you short circuit them, then it becomes the mid frequency response or midband, the small signal model. Okay, and last lecture, I guess we have started with the calculation of FL of CC1, and we have short circuited. For calculating FL of CC1, we have to short circuit the remaining capacitors and the AC source, VS, right? So that's the technique which we have to follow. And we have done this last time. And finally, we got the equation of FL of CC1 as 1 upon 2 pi R sig plus Ri into CC1, where Ri was equal to R1 parallel to R2 parallel to R pi, right? So today we will proceed ahead and do the calculations for, derive the formula for FL of CC2, that is lower cutoff frequency due to output coupling capacitor CC2 alone, right? So for this, we have to short circuit CC1, we have to short circuit bypass capacitor CE and the voltage source. So let's start doing that. So all of you, you can continue writing in your books. So what do you mean by short circuit? Short circuit means replacing that capacitor with a wire. Okay. Similarly over here, right? So over here we have short circuited the CC1 and here we have short circuited the CE basically. So now can you anyone tell me what will be the resistors RE? Will RE be redundant? Yes or no? Will my RE be redundant? Yes, na? Because it will be replaced by a short circuit. So if this capacitor CE becomes short circuit, then RE also will be redundant. So RE will be gone from the circuit, right? So in short, we have this kind of a situation wherein my emitter terminal is directly connected to the ground. So that is my situation over here. This is my, let me write over here very clearly. This is my base terminal, this is the collector, and this is my emitter terminal. Now, how do we analyze the circuit? Now, can anyone tell me what will be the impedance offered by this source over here? This source over here. What will be the impedance offered by this current source? Anyone? We have discussed this before. Now, the impedance offered by a current source is infinite. Okay, so we can write over here in bracket the impedance offered by a current source, this is will be very handy, is infinite. Okay, so what do we see? I mean, between the collector and emitter, we have infinite impedance source. So what will happen to this circuit now? Can anyone guess? What will happen now? Next. if the impedance looking into the GM into GM into V pi current source is infinite, then what will be how will the circuit represent now itself? How will it look like? Hello, am I audible? Just tell me, how will it look like? It will look something like this. So here we have open, I mean, we can draw this again. So I will be using this feature wherein it can copy this part of the circuit, okay, as it is. So let me do that. So y'all can draw it again, okay. Y'all don't have this feature, so y'all might have to draw it again. So over here I will add it like this. Now this circuit is represented by this network over here finally. Here. Okay, so this is represented, GM into V pi is represented by a open circuit. So actually this won't matter, this is not part of the circuit right now. Right now we have this much circuit only, right? So how will the system look like now? You know, remember last time we were discussing about the system wherein we have applied a input and we have a capacitance and we have a resistance over here, right? And for this type of RC network we have a lower cutoff frequency FO, where FO was given by 1 upon 2 pi R1 C1. So for this network, how will my characteristics look like? Let me show it to you. I'll use a green color to represent that. So my system will look something like this. So this is my system, right? Over here I have a capacitor, right? And here I have a RL, load RL. And then we have a output voltage, that is fine. So this is my CC2 and this is my RL. Now what I have to find out for this system, I have to find out how much is the output resistance of the system or output impedance of the system, RO. So that is what exactly we are going to do here, right? What is our system right now for us? Our system is this, no? Let me mark it over here. Sorry. This is how our system looks like, right? This is the system. So what is, right now I have to find out what is my RO. Correct. So can anyone tell me what is RO? So if I have this kind of a response, then I can say that it will have a similar kind of a characteristics. The frequency response will be described. Now, can you tell me what will be RO? Anyone? I hope I am audible because I cannot hear anyone speaking. So here RO, if you see carefully, it will be RC parallel to infinite. RO will be RC parallel to infinite. And you know that if some resistance is infinite and the value will be the lower resistance itself, so this will be equal to RC itself only. Okay, so RO will be equal to RC, and this is just the RO value, right? But in reality we want R equivalent value. R equivalent value. So what will be R equivalent value, anyone? What will be the total resistance over here, right? So we don't only have R1, we have one more resistance. So what is in the left hand side of the capacitor? Resistance RC. And what is to the right hand side? RL. So can you tell me what will be the equivalent resistance seen by this capacitor? Actually this capacitor should be CC2. Yeah. So can you tell me what will be R equivalent seen by this capacitance? Anyone? It will be RC plus RL. Okay, the equivalent capacitance will be RC plus RL. And like last time, where we have calculated equivalent capacitance only, right? Let me show it to you. Yeah, we have calculated equivalent capacitance. So what will be the time constant now? FL of CC2, 1 upon 2 pi R equivalent into CC2 now, okay, instead of CC1. So now we can write it down over here. The FL of CC2 will be equal to 1 upon 2 pi into R equivalent, which is the over here, right, into CC2. So finally, how we can write this now? Finally, so we can write it as FL of CC2 will be equal to 1 upon 2 pi into R equivalent is what? RC plus RL. So remember that how do we got it? RC parallel to RL into CC2. Okay. So this is the final formula which we got over here. Okay. And that is what we will be using as an expression. And more often RL might be or might not be given. If RL is not given, if RL is not given in the numerical, then what we have to consider? Consider RL equal to infinite, means without load. Your amplifier is not having any load at the output, right? So if RL is not given, consider RL is equal to tending towards infinity. Fine with this? This much is clear. Can someone respond, please? Is this analysis clear to you? Someone? Please let me know. Okay, fine. So I hope that you have noted this down along with me. And I'll just revise what we have done so far. So we are calculating the FL of CC2, the lower cutoff frequency due to the output coupling capacitor CC2 alone. So we short circuited CC1, CE and VS. Actually VS I forgot to do that over here, but it doesn't matter. It was an open circuit only, right? From the base point of view, from the base emitter side, it was open circuit only downstairs. If I look into it, right? So here we correlated our system and we find it out RO, where RO was RC parallel to infinite, because the impedance offered by a current source will be infinite. So we got the value of RO as RC. Then R equivalent was the equivalent capacitance seen by the coupling capacitor CC2, and it was RC plus RL, not parallel to, right? So this has to be very, very clear why it is plus. And similar to this, we have determined that this will be representing a low frequency response. So we calculated FL of CC2, which was 1 upon 2 pi R equivalent into CC2, and R equivalent was RC parallel to RC plus RL into CC2 into 2 pi, right? And if RL is not given, we'll consider RL to be, we can consider RL to be 0 actually, not infinite. If RL is not given, please substitute it over here as 0, not infinite. So please correct that. So that you have to take care that if RL is not given, consider it to be 0 in the formula, not infinite, because it will give you FL of CC2 as 0. Okay, so that's the small correction which we have made. So let's proceed forward and move on to calculation of FL of CE. So please write down, calculate FL of CE, lower cutoff frequency due to the bypass capacitor CE alone. Okay, so for this we have to short circuit CC1 and CC2 and VS. Okay, and then we have to calculate CE from here. Now okay, so let us start doing it. So what do you mean by short circuiting? So CC1 will be replaced by a short circuit, CC2 will be replaced by a short circuit, and VS also will be replaced by a short circuit. So let me do that. So here it is over here. Let me use a red color. This is short circuited, this is short circuited, and this Vs source is also short circuited. This is just for analysis, okay? Now, how will you proceed further? How will you proceed further? Again, the same concept will be there, that the impedance seen by the, current source will be infinite. So which part will disappear from the circuit? To the left hand side or to the right hand side? So this is my base, this is my collector, and this will be my emitter. So which part will disappear from the circuit? The collector side or base side? Can anyone tell me? Yeah? Obviously the collector side, because this impedance offered by this current source will be infinite. So what will remain is something like this. So you can draw it again. I will be referring to this technique. So this side will be gone. Okay. So let me just add it over here again. So your circuit will be looking something like this. Let me show it to you. How will it look like? So let me add that part. Yeah. So now I have added. So let me remove the part which was unnecessary. Yeah, because this was a current source, it will behave as an open circuit. So here it will be gone. Open circuit means gone, right? So this much is the circuit now. This coupling, bypass capacitor CE is present. Now, how will you analyze this circuit? So let me also replace this by a ground only to avoid unnecessary confusion. Okay, so this is also sorted. Okay, sorry for that. Yeah. So how will you proceed proceed in such a circuit? How will you proceed? We have to determine again over here FL of CE. Any idea? So which is the capacitor over here? The capacitor is CE, right? So we have to find the equivalent capacitor, R equivalent. So where is R equivalent? Similarly R1, right? Here it is, see here, R1. Similarly R1 will be, has to be found out over here, right? Here it is might be given, F naught is equal to 1 upon 2 pi R1 C1. Only if we know R1 C1 value we are finding it. I mean we should have that value. R1 value if we somehow calculate, then F naught will be 1 upon 2 pi R1 C1, right? So this manner we have to proceed. So related to that, now here listen very carefully. Now can I say that over here R equivalent will be this much. This will be my R equivalent. Let me mark over here like this with a red color. R equivalent will be this much. Looking into the emitter terminal. Okay. Actually, I should have no problem at all. Looking into the emitter terminal will be with this only. It will include RE also. So entire this resistance also will come. Now, can you tell me R6 is in parallel to R1 and R2 or what? Is R6 parallel to R1 and R2? Yes, it is. They are in parallel. See, the ground terminal are tied together. The other terminal is also tied together. So now one more thing is there. But this terminal is emitter and this terminal is base. So is the current flowing through emitter and base different or same? Is the current flowing through emitter and base different or same? So what is the current flowing through base denoted by? The current flowing through base is denoted by IB, correct? And what is the current flowing through emitter is denoted by IE, correct? So do you know the relation between IE and IB? Yes, you should know that, right? So what's the relation? We will write it down over here now very shortly. Okay, help me out in writing the equation. It will be IE, the emitter current should be equal to the base current plus the collector current, right? Now, what is the formula for relation between IC and IB? IC is beta times IB. Okay, or we can write it as a capital IB over here, no problem at all. Okay, fine. Now I can write the same formula as IE is equal to, if I want to write IE and IB relation, so IB plus beta times IB. So how can I write it now? Finally, emitter current will be equal to 1 plus beta. This I'll take it common, and outside the bracket I have IB. Now what does this mean? What does this mean? So can you tell me the current flowing through IE is how much? Emitter current only, no? This is emitter current only. Current flowing through RE is emitter current only. What is the current flowing through R pi? Can anyone tell me what is the current flowing through R pi? Because R pi is going into the base terminal. So how can I write it over here? What is the current flowing through R pi? Anyone? Okay, sorry for that. Current flowing through R pi resistor. Anyone can tell me? How much is that?
IB.
Sorry, IB, correct. Absolutely.
IB.
Yes, it's IB. Now, if I want to write IB in terms of IE, how will I write? So this I can approximate as, I can approximate this because beta is very much larger. I can write it as beta times IB. So are you understanding? Your current flowing over here through RE resistance is IE. Current flowing through R pi is basically, if you want to write in terms of IE, see the current flowing through this over here is, I can write it as IB. But I want to represent in form of IE current. And how will I write? Come on. So I can write it as IB is equal to IE divided by beta. Can I not? Just taken cross multiplied, right? So how can I write over here? The current is current flowing through R pi resistance will be IE upon beta. Agreed? Any problem is here? I can write it as IR pi, current flowing through R pi resistance. Any problem in understanding this? How we have written this? Yes or no? Hello? All of you have understood this? What is okay? Fine. Now, how is R pi connected to R1? If RB current flowing through R pi is IB, current flowing through R1 and R2 and R6 is also IB only, na? So what's the relation between R pi? How they are connected? Are they connected in series with R6, R1 and R2? Now tell me this. So I am writing over here. I am actually finding R equivalent. I am writing the expression for R equivalent. Okay, so R equivalent will be RE. So this RE and this will be in parallel. Everything else will be in parallel. I will show it to you. Wait. Let me use this color. All of them together. All of them will be together over here like this. Okay. Oh, sorry for that. Yeah. So now it will be RE in parallel to these things. In parallel to this tree. Now how these three resistance are related? The current flowing through all of them is IB. Correct. So now how can I write? What I can write over here, RE will be parallel to what? Anyone please help out over here? See, you have to give the answers, then you will understand better. Now, what is R equivalent given by? It will be RE parallel to what? Can anyone give the answer? Acha. tell me what is R sig and R1 R2 relation? They are in parallel, right? So can I write R sig parallel to R1 parallel to R2? Can I write this much? Now, what is the relation between R pi now? How can I write R pi? Is R pi parallel to this or in series? If is R pi parallel to R sig parallel to R1 parallel to R2 or in series? Just answer that.
Series. Series.
Yes. Plus R pi. Correct. So is this the correct expression or it is wrong? R equivalent is Re parallel to R sig parallel to R1 parallel to R2 plus R pi. Is this correct? This is wrong. What is the correct one? What you have to add to make it correct? Anyone? See, this entire resistance are in the base side, right? So the current flowing through them is base current. If I want to convert into emitter current, how will I write? Should I divide it by something or should I multiply it by something? It will be all of this will be divided by what? Anyone? Beta. All of this will be divided by beta term. Why it should be divided by beta? The same reason I R pi should be divided by beta, because you want to represent everything in terms of emitter current. So there is a conversion of emitter current. There is a conversion of base current to emitter current. So when you want to convert base current to emitter, you have to divide it by beta. Understood everyone this? How we have written R equivalent? So R equivalent is Re parallel to R sig parallel to R1 parallel to R2 plus R pi, the whole divided by beta. Because if I divide by beta, then only I can convert this as a base current. And that is in terms of emitter current. So emitter current divided by beta is my base current basically. Okay. Exact value will be 1 plus beta, but we have approximated it over here, right? And now we know this answer, R equivalent. It's just a matter of time. We can write over here finally. Next will be very, very easy. It will be FL of CE will be equal to 1 upon 2 pi R equivalent into CE. So this is the formula which we have for where R equivalent is given by the above expression. Okay. So this is the formula we have for the lower cutoff frequency of FL of CE. Right. Now, but understood this, or should I repeat any part in this? Just let me know. If anything is not clear, you can ask now. Oh, is this clear? All the steps in this? You have understood how do we have written this R equivalent equation? Okay, so next we will move ahead with this and we will see what we have to do next. So far we have calculated, just a second. Yeah, let me come back to this now. So far we have calculated and determined the relations of FL of CC1, FL of CC2 and FL of CE. We got unique expressions for each of them. Now step number 6 will be, let me add over here step number 6, over here only I'll write over here. So after determining FL of CC1, CC2 and CE, then step number 6 will be, please write it down along. Step number 6 is determining FL. Now you will say we are calculating FL only. No, you were calculating actually the individual lower cutoff frequency due to the coupling input coupling capacitor CC1, output coupling capacitor CC2 and bypass capacitor CE. Now we have to determine what is the actual FL value. Okay, so how do we determine that? How do we determine this? FL. Let me add it, let me write it somewhere else. So let me take it from here, move it from here. Okay, just a minute. Okay, just a minute. I will just delete this and I'll go down and add, because here there is less space. So that's why I will move it some other place. So after we have found out, let's say FL of CE. So yeah, step number 6. Yeah, over here in the side, I can do it like this. Yeah. So this is step number 6. Oh, sorry. Step number 6 is determining the overall lower cutoff frequency, that is called as FL. So how do we do that? So you saw basically when I plot this graph, let's say I have this graph over here with me. Okay, this is my F versus my midband gain AV. Let's say we have a midband gain AV. Okay, which is in dB, right? This will be in dB. And we have seen one of the characteristics. So let's say due to FL of due to coupling capacitor CC1, our reading is something like this. Our graph is plotted like this. Okay, let me draw it more. Okay, and due to FL of CC2, our graph is something like this. Okay, and due to FL of CE, our graph becomes something like this. Let's say, and each of them will have a cutoff frequency, right? So let's say this is 3 dB down over here. Here it is. Let's consider. Okay, this is the total and this is 3 dB down. This is the higher one. So here it is this much, it is this much point over here is 3 dB down. This is 3 dB down. Okay, now how will I mark the cutoff frequencies from here? Let me mark it from here in front of you. So I will extend it down. So this is due to, let's say, FL of CC1. Okay, next I have a cutoff frequency down. And this one is due to FL of CC2. And finally, I have the third one. Okay, and this one is okay, this one is due to FL of CE. So which we have to determine. Let's say this is the hypothetical situation. So which one we have to select? So the statement over here goes that select the highest frequency of all three. Okay, so you have to write a statement over here, select the highest frequency among all three. So what we have to write over here, we will write a statement that select the highest frequency among FL of CC1, FL of CC2 and FL of CE. Okay, whichever is the highest, you consider that as a FL. Okay, so select the highest cutoff frequency among CC1, CC2 and CE as the overall lower cutoff frequency of the amplifier. Okay, lower cutoff frequency of the amplifier. So all of them, actually, in fact, all of them will be affecting the low frequency response, as you can see, right? FL of CC, FL of CE, FL of CC1 and FL of CC2 will be attenuating at lower frequencies, right? So basically what we can say, one more line is that external capacitors CC1, CC2 and CE will affect only the low frequency response. Okay, So we can add this line also over here, that this is also important, that external capacitors now which are the external capacitors in the circuit? What we have done, CC1, CC2 and CE will affect, this is very, very important, will affect only lower frequencies or low frequency response. It will not affect the high frequencies. It will only affect the low frequencies or neither the mid frequency. So this is a very, very important conclusions we make. Okay. So any doubts in this? After we found out FL of CC1, CC2 and CE, whichever is the highest frequency among them, will consider as the lower cutoff frequency of the amplifier, which is FL. Okay. So the lower cutoff frequency of the amplifier is nothing but, I can mark over here, FL. Okay, and that is how we determine the low frequency response of the amplifier. Any problem in understanding this? Anyone? Yes or no? If you have any issues, you can ask. Any doubt you have, you can ask. Or else we'll move on to the numerical now, the first numerical. Any queries? I'll wait for your response for 10-15 seconds. Anyone has any queries in this? Please do ask. No queries? Okay, fine. So let's proceed ahead. Please mute your microphones, everyone. Okay, we will look into the numerical and we will try to attempt to solve it, right? Let's see. Everyone, please mute your microphones. Okay, fine. So let's continue now further. Let us look at the numerical.
सर ने मेरा नाम लिया लगता है, रुक जाओ 1 सेकंड, बाद में ही कॉल करते हैं, कुछ तो चल रहा है.
Okay, please keep your microphones off. Okay, fine. So module 1.1 is based on low frequency response, that is effect of coupling, bypass and load capacitance on the frequency response, right? And here these are the type of questions which they can ask you. They can ask you to draw the circuit diagram, low frequency equivalent circuit and mid frequency equivalent circuit, which we have equally seen, right? And then they will ask you explain the effect of coupling and bypass capacitor on the frequency response. So what will they do? The coupling and bypass capacitor, they will only disturb the low frequency response and not the high frequency response. Okay. So this is the numerical in front of you. We'll solve a part of it today, and I guess partly we can solve it next time. So what they are asking is a common emitter amplifier is given to us over here. R1, R2, RC, RE, CC1, CE and CC2 values are given to us. RC and RL values also given, and the beta and VB values given. They are asking us to calculate the DC parameters IBQ and ICQ. Then the hybrid model parameters RPi and GM. Then we have to calculate the lower cutoff frequency due to CC1, CC2 and CE, and then calculate the overall lower cutoff frequency of the circuit. Then calculate the midband voltage gain in dB and plot the frequency response. So this is a 10 marks numerical. Okay. So now let us begin one by one. So you help me out in writing this out. So let me open the new notebook, new whiteboard. Okay, fine. So here we will start now. Yeah. So what we have been given, let me start with black. AEC lecture 4.2, and today is like 17/1/2022. Okay, so let us start with the topic. So what they have been, we will be solving a numerical on this for BJT amplifier part. So we will draw the circuit first. So we will, let me draw the circuit first. So I will take it from the other side as it is. So let me go over here and take the circuit. You please draw the CE amplifier, this one. Please draw this. So let me add it from here, and I can paste it directly. So y'all please draw the circuit diagram again, so that you know, you have everything ready with you. Okay, so this is the circuit given to us, and we have to do slight modifications over here. So let me do that. Okay, fine. So let us start now. I'll write the values in green color. Okay, so the values over here, R1 value is 40 kilo ohms. This is around 40k kilo ohms. Then we have R2 value given as 10 kilo ohms, right? This is 10 kilo ohm. Then we have RE as 2 kilo ohm. CE value is 20 microfarad. Then we have CC2 value as 1 microfarad. See, in the exam, they might use different terminology. Instead of CC1, they might use C1. Instead of CC2, they might give C2. Right? So don't get confused. You have to follow the same technique. Don't remember the, you know, the over here, the CC1, CC2 and C, it should be this manner only. No, don't do that. This is 1 kilo ohm, and VCC value is how much? 20. It is okay. It is plus 20. Okay. And what else is given to us? RL value is also given. RL value is 2.2k. Okay. So all the values are given. The 6 resistor values and the 3 capacitors and 1 power supply value is given. Along with it, we have been given the Bjt parameters. So the Bjt parameters which are given over here are, first is beta. Beta is given as 100, and VBE is given as 0.7 volt. Okay, VBE is given as 0.7 volt. So now we have to, I mean, what are they asking? They are asking us to calculate IBQ and ICQ, GM and RPi, FL of CC1, CC2 and CE, total FL, midband voltage gain in dB, and frequency response. So let us write that one by one. What are they asking us to find? So to find, we'll go systematically. So what we have to find first, we have to find IBQ and ICQ value. Okay. Next, what we have to find out? Next, we have to find out RPi and GM. Next is, they are asking us to find FL of CC1, FL of CC2 and FL of CE. They will ask you ki individual lower cutoff frequency due to external coupling capacitors. They might use this language also. So you have to find it this manner. And lastly, I mean, we have to find the overall FL. Then fifth, we have to find the AV mid, the midband voltage gain in dB. Sixth, we have to plot the frequency response. We have to plot the frequency response. Okay, so let us start by solving this, right? So we have been given the you know, all the parameters and all the information is given to us, right? So how do we solve it? Let us start over here. Solution. So we know that step number 1 over here is DC analysis, right? So first step is DC analysis. So we by now you know the voltage divider network, right? So I no need to draw that voltage divider network directly. If it is other than a voltage divider network, then yes, you have to draw that circuit and find out IBQ and ICQ. But we have already done that analysis, so we can directly calculate that now. So now we can write it over here. Next is VTH and RTH. Okay. So VTH is given by R2 divided by R1 plus R2 into VCC. And what is the RTH formula? R1 parallel to R2. So please complete both of them and let me know the answer. We will complete first 2 steps today. Okay, so please complete it fast. So I will help you out in in this also. So you have to just use the calculator and find it out. Okay, so this will be R2 value is 10K. 10K divided by R1 is 40K plus 10K into VCC is 20. So can someone tell me the value over here? What's the value of VTH? Next is R1 parallel to R2. So that means 40K parallel to 10K. So please let me know this answers quickly. This will be in kilo ohms. Anyone? I'll tell then write down the next formula, the IBQ value, the IBQ equation. It will be VTH minus VBE divided by RTH plus 1 plus beta times RE. Now we are not deriving how do we have got this, because I think explicitly you all have done voltage divided bias many times. So I'm assuming that you all know this, right? If you want to refer how we have got this, you can refer your BC notes. So anyone please let me know VTH value, come on. And finally ICQ will be beta times IBQ. We have to complete at least 2 parts today. Everyone, please help me out in calculating this value. VTH is how much?
VTH is 4 volts.
Okay. Yes, it is 4 volts. VTH is 4 volt. Yeah, correct. Next, RTH. How much is RTH value? Anyone else? 40. Yes, perfect. 8K. Very good. So now I will substitute it over here. VTH is 4. VB is 0.7. So 4 minus 0.7 divided by RTH is 8K. Okay. Beta is how much? Given as 100, right? Is it 100? Let me check. Yeah, it's 100. So I can write 100 plus 1, which is 101, into RE. What is RE given as in the numerical? RE is 2 kilo ohms. Okay. So the value of RE is 2K. So please let me know this answer. 3.3 divided by 8K plus 101 into 2K. How much is this? IBQ. Please practice over here itself so that you don't make any mistake in the exam. Okay?
0.015.
In microamperes, tell me in microamperes. 1.5 you told, na? Is it 15.7 microamperes? Is this the value you are getting?
Yes, sir.
Yes, sir.
Okay, 15.71. And then this will be very easy. 100 into 15.71 microamperes. So this, if you multiply it by 100, it will be converted into milli, but 1 decimal there. So it will be 1.571 milliamperes. So that's the answer which we are getting. I hope that everyone is getting this. Okay, so this completes your step number 1, DC analysis. I hope everyone is writing it down along with me. Okay, let's move on to the next part. Next part is calculation of small signal parameters. This is the last part and then we'll stop today. Then we'll continue next lecture. So small signal parameter. So what are the small signal parameters? In case of your model, hybrid pi model for a BJT, R pi, oh sorry, the value is R pi. What is the formula? Beta Vt divided by ICQ. Okay, beta Vt divided by ICQ. Now what is the value of Vt to be assumed? Vt has to be 26 millivolt. Okay, always we have to assume it as 26 millivolt unless it is given to us. So 100, beta is 100 into 26 milli, that is 26 into 10 raised to minus 3 upon ICQ, which is 1.571 into 10 raised to minus 3. Fine. So 10 raised to minus 3, 10 raised to minus 3 gets cancelled. Can anyone tell me the value of R pi? I'll write the GM formula till then. So GM is ICQ upon Vt. Quickly tell. It is just a division. 1.51 into 10 raised to minus 3 divided by 26 millivolt. See students, the way I am writing, you have to write it that way only. Don't directly solve it in your calculator. You have to write these values so that you don't make any mistake at all. Because sometimes due to silly error, your entire sum becomes wrong. Anyone with the value of R pi? Quickly, your time is almost like 2:10 PM. R pi value, anyone?
Sir, 1654.99.
1.6. Tell always R pi will be in kilo ohms. So is it 1.65?
Yes, sir.
Yes, sir.
1.65 kilo ohms. Value is 1.65 kilo ohms. Okay. Now next GM value. GM value unit will be always milliampere per volt. Always remember these units won't change. Anyone with the GM value? How much it is? GM 1.57
0.0604.
in milliamperes. In milliamperes, it is 60, right? This much it is coming.
Yes, sir.
Okay. So yeah. So we have calculated DC. I mean IBQ and ICQ and R pi and GM so far. So next time I am just writing the heading. I'm
Sir,
not doing it. Yeah.
Sir, how would it be 60.42? Because ICQ is 1.57 milliamps, right?
Yeah.
And Vt is 26 volts. So
26 millivolt.
okay, yeah, I got it. Thank you.
Yeah, that's why I've told you to write this thing so that you can calculate it properly. I'm telling you the unit. See, IBQ will always be in microamperes. If you're getting other than that, then it's wrong. ICQ will always be 99% of the time in milliamperes. RPi will always be in kilo ohms and GM will always be in milliampere per volt. Please write the units properly and use this technique. Okay. So I guess I will stop over here. Next time I will just write what we will be starting with. Oh, sorry. I'm going very slow for the first numerical. Next time I won't, be so slow. So next we have to, find out FL of CC1, FL of CC2, and FL of CE. It's not a requirement that you have to draw the low frequency equivalent circuit. If they have mentioned in the numerical that you have to draw the low frequency equivalent circuit, then you have to draw it. Okay, or else for the most cases for numericals part, it's not necessary. So next time we will start with this. So next time we will complete this numerical. Okay, complete the current numerical. And let's see when we'll be also plotting the one more numerical we will cover. Okay, other than that. Fine. So similarities will be there in this numerical and other numerical, but there will be slight difference. So thank you everyone for joining. I hope that, I know I was a little slow today, but I hope that everyone has understood what we are doing over here. Okay. If you have queries post your lecture also, you all can always ask. Fine. So that's it for today's lecture, lecture number 4, analog electronic circuits. Next time we will complete the current numerical and try to solve one more numerical than that. Okay. So thank you everyone for joining.